So this is third example. We have to solve this. We have to find moment of inertia along this axis, and the axis is passing through the center of this both the masses. We can find it. So I would be first moment of inertia of this particle would be m into distance from the axis. So we assume that if it is not given, we assume that the axis is passing through the center of mass, and therefore entire mass is concentrated at the center. Therefore mass effective distance of mass from the axis is 0, so this is m into 0 square. This is 2m, and distance from the axis is 0, so because axis is passing through the mass, so this is 0 square again, so this thing is 0. Okay, so that's about mass distribution and moment of inertia. Now we shall find moment of inertia of some rigid bodies, continuous rigid bodies. This is a discrete mass distribution. We found moment of inertia of discrete mass distribution. Now we shall find moment of inertia of rigid bodies, continuous rigid bodies like hollow sphere, like rod, like ring, like disc, and everything. So let's talk about that. So let us calculate the moment of inertia of a rod. Okay, so we have to take special cases. There could be infinite cases, but we have to take only the special case, and rest all the cases we'll solve that by use of two theorems which we shall later learn, that are perpendicular axis theorem and parallel axis theorem. But now let's talk about very general cases. So first case is again if a rod of mass m and length L, and we have to calculate moment of inertia along this axis. This is the axis. Okay, we have to calculate moment of inertia along this axis. So we can call this point 0, 0, 0. Okay, and this we can call this point as L, 0. Okay, so to find moment of inertia, what we'll do is, in this rod we will move a certain distance x, and we'll take a differential element, this dx. Now if this rod has mass m and length L, what is mass density? So we can say that mass density would be, we are calling lambda, and lambda is mass upon length of rod. So every unit length has this mass lambda. Okay, so that's what we mean by mass density. So we'll cover distance x, we'll take a differential element dx, then mass of this differential element dm, this is mass of this differential element, that would be lambda, unit distance mass of rod into length of our selected segment, so lambda dx, that would be dm. And we know that moment of inertia, that I di, and this dm will have a di, and that di would be dm into x square. Okay, so this is dm into x square. Now we can write dm as lambda into dx, okay, into x square. Okay, this is di, and we know that there are infinite many di like this. So to find the net, we have to integrate this, and so if we will integrate this from 0 to I, so this will give us I, and we'll because lambda is constant for every dx, every infinite dx, so we'll take lambda out, and we'll integrate this thing x squared dx from 0 to L, because that's where it begins. It begins with 0 and ends at L. So if we'll put limit, this will be lambda into, and this will be L cube by 3. Okay, this would be I. Now all we have to do is to substitute value of lambda. So lambda is mass upon length of rod into, so this is very easy. So this cancel, and we get moment of inertia of rod along its edge, we can say at the end point. So that's the moment of inertia along axis taken at the end of rod. Okay, now we'll take another case, and in that case the axis will pass through the center of rod, and that would be somewhere axis will lie somewhere here at a distance L by 2. But in that consideration, what we have to do is the axis, we have to treat the axis. So this was the axis here, so and we treated the point of joining of axis and rod as 0, 0. So we have to treat always that axis is lying on the origin. So that will make us easy, and that will result in easy calculation. Okay, so let's calculate moment of inertia in the second case. So we have to calculate moment of inertia in this case. This is a rod of mass m and length L, and the axis is passing through the midpoint, through the center of the rod. So we can, if this is 0, so this we can call this as L by 2, 0, and this is minus L by 2, 0. Okay, so we can find the moment of inertia by same technique. Again what we have to do is that we have to go at distance x, and we will choose a differential element dx. This is dx. Okay, then the dm would be again very easy. We'll do the same calculation again and again. So the dm would be lambda into dx. Okay, and therefore di of this dm will be lambda into dx into x square. Okay, so and we'll integrate this. So let's integrate it. So we'll integrate it. So this will give us I. We'll take lambda out, and we'll integrate x square dx from now the limit shall be from minus L by 2 to L by 2. Okay, now this will be the limit now from minus L by 2 to L by 2. Let me write it more clear. Okay, so this would be lambda, and this would be x cube by 3. So I am taking 1 by 3 out. Okay, and I am taking x cube, and we'll put limit from minus L by 2 to L by 2. Okay, you can take this here, lambda by 3, and we can put L cube upon 8 minus, and this minus minus will become plus, and this we will become L cube again by 8. So this becomes 2L cube by 4. So this becomes here lambda. We can write lambda is m by L, and into 3, this extra 3 here, and this we can write into 2L upon 4. Okay, and this L cancels, sorry, 2L cube upon 4. So this, sorry, L cube by 4, because 2L cube by 8, that is L cube by 4. So this L cancels by L square. So the answer would become ml square by 12. That's moment of inertia of a rod along an axis passing through its center. Okay, so that's, I think, let me write it, ml square by 12. Okay, so that's moment of inertia. Now that's all for today, and we'll calculate moment of inertia of more continuous rigid bodies in the next lecture. So in the part B of this lecture. So that's all for today. Like, share and subscribe. Thank you.